Good morning, everybody. Hopefully you guys have had a good weekend. I know you're kind of trickling into chat for the time being, so if we're not quite there yet, it's okay. Just wanted to, sign in, make sure everything was working. If you can give me some green check marks, thanks, Taylor. And we'll get going here in a second. I have a feeling everybody will kind of be just moseying on in here in the next couple minutes. All right, so Mrs. Wood just finished up. Perfect. You love the nutrient cycle. Well, today is your day because we're going to learn a lot about the nutrient cycles. All three nutrient cycles that we need to learn in Science 10 today. I guess do a little bit of housekeeping while everyone's kind of strolling in. So we are kind of working our way through the second unit. Last week, I was hoping you would have finished the first unit, biology, and some of you did, some of you didn't. So if you haven't submitted your Unit 1 learning guide yet to get the test written, you need to get on that because that was due a long time ago. We do have a double block today, so I'm going to see how much time we can use without burning you guys out. And I want to kind of get done Unit 2 hopefully today. I know it seems like we're doing a lot, and we are, but there's a lot of material to make it through, so we kind of need to just keep rolling. And I know in math we kind of had this problem where you're like, whoa, it's just so much. But unfortunately, you just got to keep chipping away, because if we don't, then we get behind, and then that's not good for anyone. We have to go even faster. So we're going to talk about nutrient cycles. We might get to bioaccumulation, which is the third section of Unit 2. And I want to just remind you guys that instead of sitting down to doing the learning guides just before the test, it makes a lot of sense, especially with science, to kind of do them along the way. So when we go through a section each day, it's important that after I've gone through the section, you go do the learning guide, and there's the practice associated with the section. It'd be like if we were sitting in class, I'd say, hey guys, this is my presentation, I'm done. Now you guys can have some time to work. And if you do have any questions about any of the stuff in the learning guide, then ask. There's always a notes section and a practice section. And if you leave it all to the end, like Abby's just mentioning, it is overwhelming. There is a ton of stuff, and trying to remember it all at the end isn't going to be a good strategy. So chunk it up, break it down. You do, 20, 30 minutes a day, and then when you get to the end of the unit, you're done your work, you submit the learning guide, you try the review, easy peasy. So if anybody has any questions about the learning guide ever, at the beginning of class you want to ask, that'd be a really good time. And then I'd be happy to go through anything. There's one small problem today that I'm having issues with my computer loading the learning guide, so I can't write on it, but I could ask or answer questions. So I'm going to get going here in nutrient cycles, and then it is a really long section, but the bioaccumulation one is a really short section. So kind of see how much we can get done. So without further ado, here we go. We're talking about nutrients. So nutrients are basically chemicals that every organism needs to survive. And different organisms have different needs, but nutrients move through the biosphere. And remember, the biosphere is bio, is living, and then sphere. You guys know what a sphere is. Basically the biosphere is where all the life on Earth is. So it's this kind of layer on the outside of the planet, which is pretty interesting that everything lives there. And it's the biosphere. So basically the nutrients that exist, they're there, and they just cycle around. You remember, Earth is kind of a closed sphere. Every once in a while we get some little meteors landing on our planet, but generally speaking, not a lot of stuff gets added to our environment, and not a lot of stuff gets taken away from the environment for any reason. It's locked in, and that's kind of a good and a bad thing, as we'll see here in a second. And one kind of confusing thing, I don't know if it's confusing, but we call where nutrients get kind of, stored up, we call them nutrient stores. So when we think of the word store, in a non-science context, you're like, yeah, I'm going to go down to the store. Well, why is it a store? Well, they're storing things. You go to the clothing store, and they have large amounts of clothing. You go to the grocery store, they have large amounts of groceries. If you go to the nutrient store, well, that's where you're going to get your nutrients. So where nutrients are stored in the environment, we call them stores. So it's kind of a weird sort of vocab thing. It kind of makes sense, kind of doesn't. And without interference, so without human activity, generally speaking, the amount of nutrients flowing into an environment will be the same as the amount flowing out. And we'll look at how those interactions occur. I wanted to mention this because the three sort of nutrients we're going to talk about today are nitrogen, phosphorus, and carbon. But it's really kind of interesting, I think. If you've ever bought fertilizer before for plants or your lawn or whatever, you'll notice that every fertilizer has these three numbers on it. So the first one is nitrogen, the second one is phosphorus, the last one's potassium. And these three things are very important for plant life. And basically, we're going to talk about two of the three. So next time you're at the plant store, you see a fertilizer, the three numbers on it are kind of what we're going to talk about today. So with the exception of carbon. One sort of additional thing that we need to talk about is kind of how humans have impacted the environment. So basically, we wreck things. I've mentioned this before, but basically, without sort of human intervention, things would kind of just, strum along nicely. But then we get there and we pull too much nutrients out, or we pull coal or oil out of the ground, we release it in the atmosphere, and then bad things happen. So we have things like land clearing for agriculture, urban expansion, mining, industry. More people have cars, population of the world's increasing, and we basically put too much nutrients into the biosphere, which can be a bad thing. So the picture on my right here is this big open pit mine. And obviously mining is a huge thing, as is oil and gas exploration, where we dig these holes into the ground and we pull out all of these nutrients in terms of fossil fuels. We're talking about carbon and hydrogen. And then if you look at agriculture, this picture is so striking. You can see this kind of line down the middle of this forest here. And on one side of the line, there's no trees. And on the other side of the line, there's lots of trees. And does anyone by chance know what this is a picture of? Every once in a while, somebody's like, oh, I've seen that before. So this kind of brings up another really important point. The deforested section here, this is one country with one set of policies. And the picture kind of over on this side is another country with another set of policies. So it kind of separates, the sort of third world from a little bit more advanced third world. This is the border between Haiti, so this is Haiti on this side, and this is the Dominican Republic on this side. So this kind of shows sort of the human impact and how if you don't, stop sort of progression, if you allow people to cut down trees whenever they want and things like that, you end up with this massive deforestation, soil erosion, and things of that nature. So it's just kind of an interesting thing. Policies that we come up with have a huge impact on the environment. So what would animals think of that? I would go ahead and say if I was an animal, I'm thinking the Dominican Republic's looking like a pretty nice place. Unless I like open fields and pastures, then I'm thinking maybe Haiti's a nice place. We talked about biodiversity last class a little bit. I would guess that the biodiversity in Haiti is much, much lower than the biodiversity in Dominican Republic. So do the trees on the edge start to die? I don't know. If I were to guess, Ava, I would say that they probably live better because there's kind of this line where all the sunshine's coming in. If you're a tree in the big thick forest, you kind of have to get sunshine where you can find it. But if you're right on the edge, you get all the sunshine you want. So I would guess that the forest would start to creep over that border. I don't know what the actual logistics of the border, if it's a fence or just an imaginary line, but there you go. There are 5 elements essential for life on our little planet. So we talk about carbon, hydrogen, oxygen, nitrogen, and phosphorus. So these are the big sort of five. We're going to look at the nutrient cycles for carbon and nitrogen and phosphorus, because those are the big ones. And then we talk about which ones live in the atmosphere. So carbon, hydrogen, oxygen, and nitrogen are all in the atmosphere. Phosphorus doesn't exist in the atmosphere. It's not a gas, so its cycle looks a little bit different. We talk about things like carbon dioxide and water vapor, H2O. These molecules get combined in different sort of ways, and we're going to look at how that works today. So the first cycle we're going to look at is the carbon cycle. Now, this is actually in your learning guide, and it's kind of a mixed blessing, I guess. The cycles are all in your learning guide, which is awesome because it makes it really, really easy to answer these questions on tests and your final exam especially. They're basically free marks. Just like, here you go. Here's a question about the carbon cycle. And you're sitting there and you're like, awesome. I have my learning guide and I can just, go have a look at the picture on my learning guide and I can get a free mark. So the important ideas here isn't that you understand thoroughly the cycle. The important idea is that you understand thoroughly how to use the 3 pages in your data booklet that have all this information in it. So I just took the picture here just right off of your data booklet. I just took a little snip of it. And you need to kind of just understand how the carbon cycle works and how to use this information in this page. So if we look at it, it's like a map, and down in the bottom of any map, there should be a key, and this is no different. So it says carbon cycle key, and you have this rectangle. So it says anything in a rectangle is a store of carbon, or where carbon is stored, and the numbers are measured in gigatons, which is a big, very, very large amount. So if I look on the map, I see everywhere there's a rectangle and there's a number, like down here in the dirt, you have a number. So that's a store of carbon. Or right here in the grass next to the bear, there's a store of carbon. Or in the atmosphere, there's a store of carbon. So anywhere you end up with these rectangles, that's showing you where carbon gets stored. So that's the first thing you need to look at. The second thing is the up arrow, down arrow. And it says right here, carbon exchange in gigatons per year. So anywhere there's an oval with arrows going up and down, the up arrow is showing how much is getting released. The down arrow is showing how much gets stored. So basically that's it. There's only sort of 2 things you need to know off of this sheet. It looks kind of confusing. The carbon cycle is pretty easy. Nitrogen is really tricky, and phosphorus is even easier. So a couple things to note. Right here, you'll notice that there's just an up arrow. It says fossil fuel combustion. So we burn fossil fuels to power cars and electricity and things like that. And you'll notice that it's just 5.5 gigatons a year getting released into the atmosphere. There's no down arrow. So there's no kind of counter to that up arrow. So this is what we're starting to realize is leading to climate change. We're releasing tons and tons, 5.5 gigatons per year. A gigaton is, what's giga? 10 to the 6, I want to say? No. I think it's 1 billion tons. I have to check on that, Alex. Just off the top of my head, giga. So you have mega is 1,000, kilos 1,000, mega 10,000, mega, gigabyte. It might be 1 million. I'll have to look it up. You could probably find it on the internet. And then you have other things where you do have a true sort of exchange. So right here, this one right in the middle, it says plant growth releases 60,000 or 60 gigatons a year, and a decaying plant kind of locks in 61. So these are pretty well in balance, which is a good thing. Sea surface gas exchange, which is a huge one, 90-92. So 90 gets released, 92 gets absorbed. That's pretty even. And you'll notice they're all within about 10 of one another, except for the fossil fuel combustion. So everything kind of goes up and down, and it's happy, and everything's kind of in harmony. And then you get this major carbon release as a result of burning fossil fuels. So that is the carbon cycle. One thing that you'll notice over here is on this right side, you end up with coal, oil and gas deposits, and then marine sediments and sedimentary rock. So rock has carbon in it. That's 100 million gigatons of carbon being stored in rock. 100 million gigatons. That's an absolutely immense number, like huge, absolutely huge, being stored down here in rocks. And then you get things like weathering, and then, you know, carbon gets exchanged in the oceans, and deep down you get sediments, lay new rock, and then that's how carbon eventually gets trapped out of the atmosphere is, you know, deep water sediments. So the carbon can get trapped, it can get pulled out of the atmosphere, but we just keep burning it, it gets released in the atmosphere, it has to kind of exchange with the ocean gases and get trapped in the ocean, and then little, you know, marine life uses it, and then they die, and then they settle to the bottom, you get sediments happening, and then that over millions of years gets, you know, layered into new rock and pressure and things like that. So these are the carbon cycles. We talked a little bit about photosynthesis and cellular respiration. So you have animals inhale carbon. So this bear, you know, it's inhaling carbon, or exhaling carbon, I should say. The plants are creating oxygen, taking in the carbon. So you can follow the carbon. So we have carbon in the atmosphere, and then we have photosynthesis. So this tree is taking carbon out of the atmosphere. See the photosynthesis, CO2, carbon dioxide in the atmosphere. It takes it out of the atmosphere and it starts to grow. And then the little deer eats the carbon here, and then maybe the bear eats the deer, so the bear has the deer's carbon, and then the bear dies, and you can see that, sorry, there's a down arrow from the wolf here going down back into the environment. So basically the carbon that you're made up of was once part of a tree or part of, you know, some sort of organism before. You have carbon in you from dinosaurs and things like that. So the carbon just gets recycled. You know, plants take the carbon out of the atmosphere, they grow, animals eat the plants, other animals eat the animals. We talked about the food chain, and then you end up with this big cycle where that animal dies, it decomposes, the carbon goes back into the soil, and the cycle continues. Do bears eat wolves? I don't know. I'm not an ecologist. Maybe, maybe not. I'm sure you could Google it and figure it out. This is kind of an interesting map here, or I shouldn't call it a map, a graph, that shows carbon. And, you know, you can see that the CO2, so on this side is the carbon concentration in the atmosphere. It goes up and then it goes down. So this is 2004 and this is 2006. So 2005 is kind of in the middle. Why do you think the carbon in the atmosphere goes up each year and then it goes down, and then it goes up each year and then it goes down? Why is there this up and down of the carbon as it gets higher and higher? Why doesn't it just steadily increase? Why does it go up and then it comes down, and then it goes up and then down? Any ideas? Why carbon would increase then decrease once per year? Increase, decrease, increase. We're using carbon, so we're just throwing carbon in the atmosphere all the time. You drive to work, carbon into the atmosphere. All sorts of stuff. We're using carbon at a completely sort of equal rate. So why would the carbon increase and then decrease and then increase and then decrease? It's a tricky question. I'm hoping this works. I linked it right from YouTube. We won't get, or maybe we will get audio. I'm going to just sit really close to the speaker here, and hopefully you guys can pick up the audio through my mic, because we don't have this thing wired very well. But this is a pretty interesting little video, so we'll see if this works.
dioxide is a naturally occurring gas in our atmosphere, and monitoring it is like watching our planet breathe. This animation shows the seasonal cycle of carbon dioxide and the increase of carbon dioxide every year due to human activity. In photosynthesis, plants absorb sunlight and carbon dioxide to make oxygen. And in what's known as respiration, plants produce small amounts of carbon dioxide that is released back into the atmosphere. When we burn coal and fossil fuels, lots of carbon dioxide is released into the atmosphere. Carbon dioxide is also a greenhouse gas which traps infrared radiation and helps keep the planet warm enough for human life. NASA's Atmospheric Infrared Sounder Instrument, or AIRS, is an instrument on NASA's Earth-orbiting satellite called AQUA. AIRS can measure the concentration of carbon dioxide in the middle of the atmosphere around the entire globe every day. In this animation, orange represents carbon dioxide as measured by AIRS. Green represents the concentration of vegetation measured by another instrument on the AQUA satellite called MODIS. Here we've taken out human sources of carbon dioxide to see the natural cycle of the gas as it's affected by the seasonal photosynthesis and respiration of trees and plants around the globe. Carbon dioxide builds up in the northern hemisphere during the winter months when trees and plants are losing their leaves, and in the summer when greening occurs, plants, through the process of photosynthesis, absorb the carbon dioxide from the atmosphere. This process can be seen particularly well in the boreal forest of Asia and North America, located in the northern regions of these continents. This is the first direct observation from satellite instruments of the breathing of the global biosphere.
Just out of curiosity, how was the audio on that? Could you guys hear it kind of okay, or was it really kind of muffled? I don't think we have a better way to do that quite yet, but we'll figure it out eventually. Yeah, it was fine? Okay, that's great. Good to know. So if I just take a step back now. Yeah, everyone says good. That's great. So the increase and decrease is due to the seasons. If you look at the landmass of North America, it's all in the landmass of Earth, it's all in the northern hemisphere. So when we have sun, all of the plants start to grow and they absorb all the carbon out of the atmosphere. And then they're living, the carbon in the atmosphere is really low. In the winter, all of the trees drop their leaves, all the plants start to die and decompose, and that carbon breaks down and goes back to the atmosphere. So Earth actually breathes. It exhales carbon in the winter, and then when it gets warmer and sunnier in the northern hemisphere, it inhales it in the summertime months. So it's this constant exhale, inhale each year, each trip around the sun. So that's why it goes up and down in these really noticeable pattern. I'm not going to get into global warming, climate change too much. I will, mention it every once in a while, but there's many things that cause it, and there's many factors that lead to it. We can talk about sun cycle, perturbation of Earth's orbit, the eccentricity of Earth's orbit, sunspots cycle every 12 years. There's many natural causes of climate change, and there's many man-made causes. So I'm not going to debate which one is which. One other thing that a lot of people don't realize that I always find fascinating is how people get their energy needs. So you go to your house and you plug in your computer and you turn on my science lesson. Where's that energy coming from? Well, if you live in British Columbia, you can see that the majority of BC's energy comes from hydroelectric. And as you kind of go across Canada, you see that different provinces use different methods to generate their electricity. So Alberta, because they have oil sands and lots of coal reserves, they burn coal. Still, 2016, they're still burning coal to generate electricity. They don't have lots of mountains. They can't use hydroelectric dams like we can in BC. You go further, you'll notice Ontario has a lot of nuclear power because, again, they don't have lots of mountains to trap water, to use that, gravity sort of thing. Quebec has a few more dams. Obviously, their energy needs are almost all hydroelectric and nuclear. And you can see even like Nova Scotia has some coal-fired power plants and things like that. So it's always amazing to me to think that even Alberta, Saskatchewan, nowadays are still burning coal to generate electricity. So here's kind of an energy production breakdown for Canada. You guys probably can't see the bottom here. The purple on the bottom is coal. The big blue one is burning oil. The green one is gas. The yellow one is nuclear. And then the top ones are geothermal and renewables. So that's not too bad. So you can see as time goes on, we're getting away a bit from oil, but not really. You end up with these renewables and nuclear kind of being kind of consistent, but as more people live in Canada, you end up with these big amounts of burning gas and oil and coal. How does burning coal generate electricity? That's a great question. Generally speaking, all of these processes are almost identical. You get a big turbine, it's kind of like a fan, and you spin the fan, and that generates electricity. So if you're in a hydroelectric dam, that big fan is spun by water. It rains, water flows through the dam, spins the turbine on the way, creates electricity. If we're using nuclear, coal, gas, if we're burning anything, we're creating heat, we usually take water and we heat it up until it turns into a gas. And then that gas has a high pressure, and that pressure is enough to spin a fan. And then we cool the water down and loop it back around and just keep spinning the fan by heating up water to create steam. So that's how you're looking with any sort of burning or nuclear, same idea. So, and then you can have wind, which spins literally a fan. And there's all sorts of ocean current stuff and things like that. But generally speaking, you're heating up water to spin a fan in a very simple method. Which one is most efficient and the best for our environment? That is an extremely difficult question to answer. Efficiency, I shouldn't say, is difficult to answer. I'm sure there's actual statistics on which one's the most efficient, but best for the environment, that's a tricky one. Because if you look at just the immediate sort of stuff happening, it can be kind of easy to say, well, you know, hydroelectric just has a dam and you create the energy. But to create that dam, you had to flood a valley, which is kind of in the news right now. There's something called the Site C Dam project up in northern British Columbia, where the government wants to build this huge dam and flood a valley, but there's lots of farmland in the valley. There's lots of First Nations sort of heritage sites in the valley. So it's kind of has these huge environmental impacts. When we burn coal, we have to dig a hole in the ground, take the coal out, and then we burn it, and that increases the CO2 into the atmosphere, so that can be considered bad. I don't think there's any sort of good way of generating electricity without sort of damaging the environment. Solar, perhaps, is getting to be more efficient and less bad for the environment. So you end up with, it's debatable. There's no right answer to it. This is the United States, and because they're our neighbor to the south and their population is about 10 times as large as ours, they have these huge energy requirements. And you can see that about 34%, or you can't, there you go, thank you, Mr. Ross. About 34% of electricity generated in the United States is still coal, and 31% is natural gas. So for 65% of the energy in the United States, they are releasing carbon dioxide into the atmosphere. The other is renewables, nuclear. Renewables can be things like hydroelectric, wind, solar, and nuclear, very small little chunk of the pie. So always interesting to know where your energy comes from. Everyone just kind of says, oh, you know, turn on the lights and you're good. Well, that has to come from somewhere. So carbon storage. Short-term storage can be found in aquatic organisms, so little tiny microorganisms that live in the ocean. They absorb CO2 and they eventually die and settle to the bottom of the ocean, and they create new rock in a few million years. And you get that sort of layering, so you get sedimentary rock happening. Longer-term storage, you get in the middle and lower ocean layers, and sedimentation is kind of the main storage of carbon, the main trap of carbon. You can get things like forest floor, decomposing carbon happening there. A plant takes carbon out of the atmosphere, it dies, it falls over, it decomposes, it goes back into the soil, and then you get plants retaking it up again. And then if you have massive forests that die and they get trapped in immense pressure and things like that, you can get those hydrocarbons, those plants, turn into coal and gas and oil over millions of years. So those are also traps of carbon. There you go. Do you think in the movie Interstellar, always interesting to get movie talk in here, carbon and nitrogen could take over our atmosphere? I'm not sure. Well, nitrogen is kind of the main component of our atmosphere, so that's not too hard to believe. Carbon, I don't know. It's a very small percentage right now, but has a big impact. So I'm not sure what the answer to that is. Over a long enough time period, possibly. We talked about photosynthesis before. Photosynthesis takes the carbon out of the atmosphere and it traps it in a plant. And then you eat the plant and you get the carbon in you. So basically all the carbon that's in your body came from a plant somewhere along the line. If you're a vegetarian, a plant grew, you trap the carbon directly from the plant. If you're eating an animal like a cow, well, the sun shone on the grass grew, trapped the carbon, the cow ate the grass, you eat the cow. So now the carbon from the atmosphere went into the grass, into the cow, and now into you. Or if you're eating a tomato, that plant is just trapping carbon, creating a tomato. You eat the tomato, you now have the carbon in you from the tomato. So you need carbon. Everything in your body is made up of carbon. You're a carbon-based life form, and all life forms on Earth are. So I shouldn't say that there's some bacteria and things that are debatably not, but the majority are. So there you go. Photosynthesis traps the carbon, and then the opposite process is cellular respiration. So we take that carbon, we take those sugars, we burn them in our cells, in our mitochondria, and then we get energy from them. Energy to heat our bodies, energy to allow us to move, energy for us to do things like talk and listen and see. All of our cells need this energy. So we talked about it before. The cellular respiration formula and the photosynthesis formula are complete opposites of one another. So we're kind of revisiting that same idea again. But now we're talking about specifically the carbon. So that carbon cycle, we take the carbon, we burn it, we release it back into the atmosphere, we exhale carbon, and then, you know, a plant outside my office here is going to take my carbon in, and it's going to grow, and then the deer is going to eat that plant, and then, you know, the carbon cycle continues. The deer is going to get eaten, or the deer will die, and then the carbon will break back down. And at every step along the way, you end up with these decomposers. So the decomposers, the detrivores, they break down the old dead things, and it allows the carbon to go back into the atmosphere, back into the soil, so this carbon cycle can continue. Without the decomposers, all living things would still be sitting here on the ground, and, you know, they just pile up. I talked about it last day. They're really important, super, super important decomposers. They return all the nutrients back, not just carbon, but all the nutrients back and cycle around to enter the cycle again. We also have these ocean processes. CO2, carbon dioxide, gets absorbed in the cold air up at the North Pole and the South Pole, and then it kind of cycles back towards the equator, it rises up, and then gets released in the atmosphere at the equator. Why the equator? Well, the equator has all these tropical rainforests, and it readily consumes all this carbon. So this carbon cycle just keeps going in the oceans. The cold water, all of the CO2 gets absorbed, it falls down to the bottom of the ocean, goes along the bottom to the equator, brings all these nutrients to the tropics where it's really warm. That water is warm, so it rises and releases the CO2 out into the tropics, and the cycle continues. So this is how the ocean currents cycle that carbon constantly. And then we have CO2 levels due to volcanic activity. Just when you thought you had a grasp on it, well, there's volcanoes. And we've been pretty lucky in the last couple hundred years to not have any sort of major volcanic eruptions, but there's been a few. So you can see every time a major volcano erupts, like in 1965, or there's another one here in about 85, and then Pinatubo erupted, well, probably around the year you guys were born, late 90s. You can see the CO2 levels increase as you end up with these huge volcanic eruptions. So volcanoes release millions and millions and millions of tons of carbon dioxide into the atmosphere each year when you get a major eruption. So that contributes to the carbon cycle as well. The eruption happens, the ash cloud sort of goes into the atmosphere, and then that carbon's needed to absorb into plants and things like that. So it's not just lost, but there you go. All right, so human impacts. Those are kind of all the natural processes. You have this ocean gas exchange, volcanic eruptions. These all happen without our help. But how do we mess up this cycle? What do we do? Well, we talked about it a little bit already. So since the start of the Industrial Revolution about 160 years ago, carbon dioxide concentration in the atmosphere has increased by about 30%, which is a lot when you consider it. Every year before that, it increased by about 1%. So this 30% is a big jump. CO2 is a greenhouse gas, and don't get me wrong, as that video we watched a second ago said, we need greenhouse gas to keep our planet warm. Without CO2 in our atmosphere, our planet would be cold and we'd all die. There wouldn't be liquid water. It'd be a bad scene. So we need this CO2. It's necessary for life, but we've added too much to the atmosphere. So farmed land doesn't remove as much CO2 as like a forest would, and we run into these sorts of problems. Pardon me. I'll leave that up for a second to make sure you guys get it down. So this is kind of the human impact of adding carbon to the atmosphere. We'll look at a couple little charts here in a second that shows kind of how this affects our planet. You guys have probably seen some of these things before. All right, so this is a graph taken from NASA. So we're gonna go that it's a pretty credible source. The orangish line here is the CO2 levels going back to 400,000 years. So we're going back a long time. And it goes up and down and up and down and up and down and up and down. And there's this magic kind of 300 parts per million. And this is about 1950. And we're actually a bit higher than this right now. So this kind of shows you the amount of carbon dioxide that's been released into the atmosphere as a result of us. Take that for what it's worth. I'm not going to say much more about it than that. So there you go. So that's the carbon cycle. Does anybody have any questions about the carbon cycle? This cycle stuff is dry. It's boring. I don't love it, but it is part of the curriculum, so we have to go through it. There is some important ideas that come out of it, but it's generally speaking pretty boring sorts of stuff. All right, the next cycle we're going to look at is the nitrogen cycle. Nitrogen is a very important part of DNA, and all organisms, most organisms contain some amount of DNA. So we need it for DNA, some proteins, things like that, muscle functions, and there you go. So nitrogen is important, and this is the most complex cycle of the three we're going to talk about. So yeah, DNA is great. Our atmosphere, I'll go back to that slide in a second, but a lot of people don't understand. They think, oh, we breathe oxygen, we breathe out carbon dioxide. Our atmosphere must just be full of oxygen. And I know you learn it along the way, but often you forget it. So this is all the planets in the solar system. Here's Earth right here. Our atmosphere, the air you're breathing right now is mainly nitrogen. 78% of what you're inhaling, ooh, that was good. There's nitrogen. That's all nitrogen in there. Very little of it's oxygen, about 20% of it. And then the rest is kind of argon, water, some carbon dioxide, but nothing really in terms of anything else. So every breath you take, 78 plus 21, that's 99%. Right there, 99% of what I just inhaled was nitrogen and oxygen together. The rest, that 1%, is carbon dioxide and argon and other gases that kind of exist. So if you look at some of the other planets, Mercury has a lot of oxygen, but there's some problems with Mercury because it's not really an atmosphere because it's not quite as thick as ours. Well, it's not thick at all. So Mercury's there. Venus, a lot of CO2 on Venus, pretty hot there, a little bit of nitrogen, a little bit of acid in their atmosphere, which kind of isn't good for life. We look at Mars. You see that Mars is about 3% nitrogen, about 95% CO2, and then argon. So their atmosphere on Mars is kind of similar to Earth, minus the oxygen and nitrogen. And then the gas giants are just made of gas, so they're mainly hydrogen, all of them. So there you go. That's kind of a breakdown of planets. Sorry, I was kind of reading chat kind of coming up here. Dean is great. What would happen to us if if all of a sudden 78% oxygen and 21% nitrogen, everything would light on fire? That's what would happen. The whole Earth would just burn instantly. If you get concentration of oxygen that high, when you're like rolling around your blankets at night and you get those little sparks and stuff when it's really dry? Well, it would just light your blankets on fire. That's what you need to burn things. That's what's going on, is oxygen's getting burnt. So if our atmosphere was 78% oxygen, it would just all burn and then we would all die. It wouldn't be a good scene. Gas giants are kind of like stars that never happened, really. If they had a little bit more mass, that hydrogen would be able to fuse together and create stars, but they're just not quite massive enough to become a star. So that's what stars are mainly made of, like the sun is mainly hydrogen. And you're right, Abby. You can increase the amount of oxygen. You'll see even, sports athletes like football players will, run their shift or whatever on the field and then come off the field and then put on the O2 mask to get higher amounts of oxygen. Some interesting stuff if anyone has a scuba diving license. When you're talking about going to different depths, they add different amounts of nitrogen and oxygen to your tank so you won't end up getting something called the bends. So we know, the human body's sort of limitations and how much oxygen's good for it and how much nitrogen's good for it. And we can add other gases like helium in there to make things happen. So there you go. Oxygen is bad. It is good. We need it to live, but it does burn. That's part of combustion reaction, and we'll talk about that a little bit later. Why are the terrestrial planets all located in the inner ring and the gas giants in the outer part? I don't know, to tell you the truth. I'm sure that some bright astronomer would be able to inform you of that, but I don't know why all the terrestrial ones are there and the gas giants are all on the outside. Just kind of maybe the way things formed. I have no idea. I'm sure you could look it up though. So the problem with nitrogen is our atmosphere is nitrogen. It's N2. It's one nitrogen atom, two nitrogen atoms. They bond together. You get N2. Our bodies can't use N2. I can't inhale nitrogen out of the atmosphere and use it in my body. My body isn't absorbing the nitrogen. Well, it is a bit, but it isn't using the nitrogen I absorb. So the nitrogen that you're taking in constantly in your lungs doesn't go into your body. It doesn't go into your cells that way. The nitrogen that you have in your body is all because of the food you ate. So how do we get the nitrogen from the atmosphere into our bodies in a usable form? So let's look at how that works. It's called the nitrogen cycle. Basically, the nitrogen, if you want to think of it this way, in the atmosphere is broken. Think of it as being broken. I can't take it in my body. It's in the atmosphere. I'm inhaling it, but it's not entering my cells in a form that I can use. So it's broken. So what has to happen first? We have to fix it. If something's broken, you need to fix it. So there's a process called nitrogen fixation. It takes that nitrogen from the atmosphere and it converts it to something our bodies can use. There's nitrification, and then the plants can take this stuff up. So in the atmosphere, we have N2. It's two nitrogen atoms bonded together. In the soil, bacteria breaks down the N2 into these two things called ammonium, and nitrate. We're going to talk a little bit about ammonium and ammonia. They're both part of the nitrogen cycle. Nitrogen cycle is a tricky one. Sorry, grabbing a drink so I don't cough on you guys for the rest of the day. So ammonium and nitrate, we're going to look at these in a second. You don't even need to memorize these because they're on your nitrogen cycle. This is the greatest thing, right? All of these really crazy vocab words, it's just there. It's in your data booklet. It's gifts. It's a gift for you. Here's some free marks, is what teachers are saying to students when they ask you questions about the nitrogen cycle. So here's the nitrogen cycle. It's in your data booklet. When you get your data booklet for your provincial exam, it's in color. This makes it a little bit easier to follow. It is complex. I'll be the first to admit it. It's way more complex than the carbon cycle, and the phosphorus cycle is just like easy peasy compared to this. But it's pretty straightforward if you can follow some arrows and figure out where everything's going. So we know that all this stuff around me is nitrogen, and it's in the atmosphere as N2. So let's start there and let's see if we can kind of follow it around. So up in the atmosphere, you can see at the top here, the start of this blue arrow, the atmospheric nitrogen is this N2 with traces of NH3, NO, and NO2. So we're not going to worry about these last ones right now. It's primarily N2. Remember, 78% of atmosphere is N2. We can't use it this way. It's broken. So what do we want to do it? We want to fix it. So you can see the blue arrow down here on the side. We have nitrogen fixation. We're fixing it. So basically, nitrogen fixation is bacteria in the ground are taking the N2 from the atmosphere and they're converting it to NH4. So this is the ammonium that we're talking about. So that's kind of the first step. Now some plants can use that. Awesome. These plants are growing, they can use it, they're taking that NH4. But you end up with another process happening, converting the NH4 into NO2 and NO3. It's a two-step process. It's called nitrification. And again, do you need to memorize this stuff? No, it's on your data booklet. It's just a gift. So nitrogen fixation takes the N2 from the atmosphere, breaks it down into NH4. Some plants can use the NH4, but plants also like this NO3. So basically, again, some bacteria takes this NH4, it's called nitrification, in a two-step process, converts it to NO2 and then NO3. And from there, it goes up this green arrow into plants. So the plants use the NH4 and the NO3 and NO2 to grow. So that's kind of the first thing that's happening. You can see the kind of the pink arrow is this denitrification, which means there's bacteria that also convert that NO2 and NO3 back into N2 into the atmosphere. So it's completing the cycle, which is kind of cool. There's lots of other things happening. So you can see right here, this kind of green bubble right in the middle. This is adding fertilizer. If you want to grow something and there's not enough nitrogen in the soil, you add fertilizer to the field. So that's a kind of a human way of adding more nitrogen to the cycle. We create fertilizer, we put it on our fields so we can grow plants. Oh, wow. All right, so there you go. Those are kind of the main process. You have this nitrogen fixations taking the atmospheric N2, converting it to ammonium, NH4. You also have nitrification, which is the second process that happens, which converts the NH4 in two steps to NO2. And again, this is all in your diagram. You can get sedimentation happening and uptake by plants behind my head here. So that's another process that's kind of occurring at the same time. Another way, which is really cool, I think, another way that nitrogen gets fixed, you can see it up here, atmospheric fixation. Lightning. Lightning can take the N2 in the atmosphere and convert it to this NO2 and NO3 that all of these plants need. So it happens during lightning, and you're like, well, there's not that much lightning happening right now. You know, Kelowna hasn't got struck by lightning for a long time. We haven't had a lightning storm since probably fall or spring or summer. Well, Every second on Earth, there's about 6 lightning strikes happening. So right now, boom, 6, 6, 6. Every second, the Earth gets struck by lightning about 6 times. So a lot of around the tropics and things like that, but it is happening. So it is worth mentioning. So bacteria can fix nitrogen, lightning can fix nitrogen. Those are kind of the two things that takes nitrogen from that atmospheric useless stuff to the stuff we really need, that NH4 and the NO3 and NO2. So that's the nitrogen cycle. It is confusing. There's lots of stuff going on. We have volcanoes releasing it. We have, factories putting it into the atmosphere in different forms. It changes forms though. That's why the nitrogen's so hard to follow, because it starts out as N2, and then now it's NH4, and now it's NO2, and now it's NO3, and then the cycle just keeps going. And then you have the green arrows, and the blue arrows, and the pink arrows, and you're trying to figure out what everything is. If you just concentrate on the kind of the blue arrow on the outside, that's kind of the main process that's happening. You also have this little bunny here. Animals will die. They'll get broken down by the detrivores, the decomposers, and their nitrogen will go from, being nitrogen in my body and going back into the soil to be taken up by more plants. So that happens as well. There's lots of stuff going on, but I'm confident you guys can follow this diagram. You guys are really good at reading graphs, and it's kind of like a graph. The nitrogen cycle's a bit tricky, but there's not the big stores of nitrogen like there's big stores of carbon. It's just constantly being cycled. So that's pretty cool. So there's the nitrogen cycle. We talked a little bit about nitrogen fixation. This is kind of the notes that goes along with it. Again, a little bit dry, but what are you going to do? So nitrogen fixation, think about it as nitrogen's being broken. N2, it's broken. We need to fix it to use it. So you end up with getting this nitrate and the ammonium. The problem is the N2 can't be used by plants or any organisms. So we need this NO3, we need the NH4. So the nitrogen's kind of switching what it's being bonded with in order to allow us to use it. So basically all of agriculture depends on being able to take atmospheric nitrogen, the N2 that's all around us, and converting it into something that plants can use. So if you have nitrogen in your fertilizer, it came from the atmosphere, they just change what it's bonding with so they can turn it into a solid and put it on a field. I'm not going to go into too much detail with the rest of this, so I'll just let you guys fill in the blanks. It is a lot of stuff going on. It's not super exciting, very dry, kind of boring stuff, but it is important. Again, the two things that fix nitrogen are lightning and bacteria. And the rhizobium bacteria is the main one in soil. And basically, to make life really easy for plants, they grow right on the roots. So these plants will create these conditions for this bacteria to grow right on their roots, so the plants can just convert the nitrogen into the stuff they need right at their roots, which makes life easy for the plants. There are types of bacteria that can do this too, kind of along with photosynthesis. So there you go, that's nitrogen fixation. That's taking it out of the atmosphere, making it into something that plants can use. So that's kind of the first step in the journey. The second step is nitrification. And nitrification is again occurring in bacteria. It's taking that ammonium, the NH4, and converting it into NO3, nitrate. It's a two-step process. The NH4 gets converted to NO2, and then it gets converted to NO3. Do you need to memorize this? No, it's on your data sheet. So you just need to be able to find it. So my biggest piece of advice to you in this section is all of these words, nitrification, nitrogen fixation, denitrification, they all sound the same. They all have that root word nitrogen, so it's really confusing. So all you need to do is familiarize yourself with your data booklet sheet. Can you, looking at that nitrogen cycle in your data booklet, can you find the word nitrification? Perfect. What's at the start of the nitrification arrow? What's at the end of it? Well, it starts on the left with NH4, and then if you follow it along, it ends with NO3. So that's nitrification. That's the process. You don't need to memorize it. You don't need to know what nitrite and nitrate are, although they're both in your data booklet too. But you can see that it starts at NH4 and it converts it to this NO3. And it's on your sheet. No memorization required. Coming back to this picture of this plant that I had before. So basically plants take up the NO3 and the NH4. They need both of these things to grow. And you can see them absorbing it, and it grows into a plant. How do you get the nitrogen in your body? Well, you either eat the plant that has the nitrogen in it, or you eat an animal that ate the plant. So again, this is the cycle. Plants take this stuff up. We need nitrogen to grow. All of our cells have DNA in them. Not all of them, most of them have DNA in them. And that DNA has nitrogen in it. So in order to replace your DNA, your body needs to constantly take in nitrogen. And that nitrogen is coming from the plants you're eating. It's also coming from the animals you're eating. So that's how your body takes in this stuff. So that's the nitrogen cycle. How does nitrogen make it back to the atmosphere? This is kind of one of these important ideas. If you could imagine there was no process that returned nitrogen back into the atmosphere, the nitrogen would get sucked out of the atmosphere and get trapped in plants, and then there wouldn't be any nitrogen left. And Abby, yes, ammonium is in cleaning products. Ammonia is kind of a similar chemical composition, and that's what you're probably talking about. So there has to be some process which returns the nitrogen from the soil back to the atmosphere, else it would just all get pulled out of the atmosphere and there'd be none left. And our atmosphere would be oxygen and something else, and it just would be a bad scene. So basically, there's a process called denitrification, or you have bacteria that are denitrifying bacteria, which takes the NO3 from the soil and converts it back to N2 to enter the atmosphere again. And without that bacteria, all that nitrogen would get trapped in the soil, and we'd never see it again, which would be a problem. So there you go. How do we mess this one up? Well, we burn fossil fuels, and that releases lots of this bad stuff into the atmosphere, causes acid rain and stuff like that. So yeah, so that's kind of the nitrogen cycle in a nutshell. It can get trapped back in rocks again and things like that once it enters the sort of water systems, and that's not always a bad thing, but high levels of nitrogen in water can lead to some bad situations for aquatic animals. I have a little fish tank, a little 10-gallon one at home, and basically every once in a while you have to take a sample of water into the store and you say, hey, can you test this? And every once in a while a guy will say, hey, you got a lot of ammonia in your tank. And what that means is there's not enough bacteria taking that ammonia out of my tank, so I have to add a bacteria supplement to my tank so the plants, the animals in there, and all the water and all the bacteria that lives in there can start changing that ammonia, changing that nitrogen into something the plants can use. How do we screw this cycle up? Here we go. We can burn fossil fuels to increase the amount of nitrogen. We can put too much fertilizer on fields, which leads to runoff into our waterways. And there's this word, I don't know why it's such a popular word, it's eutrophication. You can see it over here. And basically, eutrophication is excess nitrogen causing these kind of algae blooms in the environment. And it's a word that kind of pops up every once in a while. And I guess it's kind of important. It's one of our vocab words, so you should know what it is. It doesn't show up on the data sheet. It's kind of one of these ones you just need to know. I've seen it on some provincial exams before, that's why I mention it. But definitely something you won't encounter in sort of everyday life, eutrophication. But there you go. Now you know, you're aware, it's there. Give you guys a second for that one. I guess the main impact we have is by putting fertilizer on our fields. If it doesn't get absorbed by the plants, the fertilizer gets rained on, the rain runs into streams, runs into rivers, runs into oceans, increases the amount of nitrogen in our waterways, which is a problem. All right, phosphorus cycle is the last one, and then we'll take a break and jump into the next topic. I had some pictures here that didn't load. Maybe they'll load in a second. It's too bad. Sorry, I'm jumping around so much. Phosphorus cycle is the last one. Where does it say eutrophication? Right here. Sorry, it's the first point in the bottom paragraph. This promotes huge growth of aquatic algae known as eutrophication. Excess phosphates in waterways is another cause of eutrophication. So too much nitrogen leads to eutrophication, too much phosphorus leads to eutrophication. And that is just these huge algae blooms that end up getting caused by excess nutrients in the water. Phosphorus cycle, compared to the carbon and compared to the nitrogen cycle, is a really easy one. So basically our cells need phosphorus. There's not much more to it than that. It helps root growth in plants, healthy stems, and seeds in plants. Basically your bones are mainly made of calcium and phosphorus, so you need it for healthy bones. The great thing about phosphorus is it's not stored in the atmosphere, and it's basically stored in rocks. You're thinking, can't remember the last time I had a rock for dinner, so I must get it into my body some other way. And you would be right by saying that. So here's the phosphorus cycle, and you're like, whoa, it kind of looks complex, and you got layers happening and things going on. It's easy. There's almost nothing going on here compared to the last two. So again, you have a key down here in the bottom. Anything in a circle is millions metric tons per year, and anything in a rectangle is something being stored. So we have stores in rectangles and then transfers in circles. So there's your key. Everything's kind of being measured in millions of metric tons. So if we look at the whole big picture here, phosphorus. So we're talking about P on the periodic table, phosphorus. Basically the important thing is right here in the middle, we have the cycle happening in our oceans where we get the water dissolves, we have weathering happening, dissolves phosphorus from rocks, and it enters the water. And then the fish eat the plants, and the plants absorb the phosphorus, and it enters the food chain through plants, taking it in out of the water. So that's the aquatic sort of phosphorus cycle. It gets dissolved in the water, the plants take it in, animals eat the plants, that's how the phosphorus gets there. On the land, we have the same sort of things happening. There's phosphorus in the soil, that gets taken in by the plants, and then the deer eats the plants, and then the deer dies, and it goes back into the soil. It gets decomposed, and you get this phosphorus cycle right here happening on the land. There's some other things happening. Industrial waste up here at the top adds 2 million metric tons per year. Bird guano islands, so bird poo has a lot of phosphorus in it. 7 million tons gets added to the system from bird poo alone. It's considerable. Weathering. So we have rocks. They get dissolved into sand, into streams. It enters the water, and then basically that's how you end up with phosphorus in there. There's other things happening down in the bottom right corner. It's kind of sort of more complex, but phosphorus basically gets stored in rocks. So we can mine phosphorus, and we do mine phosphorus. Earth's crust has, 20 billion million tons? 20 billion million tons. That's a lot. Ocean sediments have 100 million billion, or 100 million tons. That's a big number too. There you go. So that's the phosphorus cycle. I won't spend too much time on that one. It's pretty straightforward. There's not a lot going on there, and generally speaking, students have a pretty good idea when they can just look at it. There's stores, and then there's transfers, and that's about it. So that's the phosphorus cycle. The important idea here is that rocks are the main store of phosphorus. And in order to get that phosphorus out of rocks, you have something called weathering. So we talk about weathering as a result of wind. We talk about weathering as a result of precipitation or rain. So those are sort of the two big causes of weathering. Basically, it gets dissolved in the rocks, and then that water runs off somewhere, and either a plant grows and takes in the water, or you have some sort of animal eats, drinks the water, and then dies, and then the plant's bacteria decomposes it, and then the phosphorus enters the system that way. So there you go. That's kind of how phosphorus enters the cycle. These were the images I was looking for before. Apparently I've gone crazy. Basically, we add phosphorus to the cycle. This is how we mess up this cycle. We add all this phosphorus through mining for fertilizers. We know we need to create these fertilizers to grow all the plants we like to grow. If you imagine not using fertilizer, think about all of these cycles we've talked about today: carbon, phosphorus, nitrogen. If you had a field full of plants and you kept growing these plants year after year, all those nutrients would get taken out of the soil. Imagine, keep it really simple, something like a field full of wheat. So just, wheat, this type of grass growing. Every year you come through, you cut all the wheat, and then what's left? Well, it's just soil. You plant your wheat again next year, you come, you take it all off. You're not leaving anything on that dirt for nutrients to re-enter the soil. So how do you get nutrients in the soil? If you could imagine after a long enough period of time, I don't know what the number is, but we'll just pretend it's like 10 years. After 10 years of growing wheat on a field, there's no nutrients left in that soil. You've taken all the phosphorus out of the soil. You've taken all the carbon. You've taken all the nitrogen out. There's nothing left there. So no plants would grow, literally none. So we have to add fertilizer to the field. What happens is that fertilizer gets put on the field. Not all of it gets absorbed by the plants. It rains, it runs off into streams and rivers, and then you get these kind of algae blooms you can see next to me here. So the one on my right here, this is a small, just like a plant. This is, sorry, not a plant, a small pond. This is eutrophication happening. So you get these really thick green algae blooms as a result of excess nitrogen and phosphorus from fertilizers. And that basically blocks out all of the light entering the pond, and nothing can grow. So it just kills that whole pond because no light can enter it. It creates a toxic environment for plants. On my left here, this is a big sea, and this happens in places like Lake Erie and the Great Lakes as well. This is eutrophication from space. You can see this huge green algae blooms starts to block out light, and you end up with sort of dead waterways as a result. So that's how we screw it up. And yeah, this does happen around your neighborhoods for sure. You get these really thick algae growths in some of these ponds, especially in the summer when it's really warm. The conditions are right, and it can block out light, and it can kill a lot of other plant species in these tiny little ecosystems. We used to have a huge problem with detergents. You can see kind of behind me here. Laundry detergents used to have a lot of phosphate in them because it helped clean your clothes really well. So for a long time, companies would just throw tons of phosphate into these laundry detergents, and that would eventually enter the water system, right? You drain your washing machine, goes into the sewer treatment treats it, but eventually it gets put back into a waterway, and they didn't pull the phosphorus out. You end up with really elevated levels of phosphate in the waterways. Toronto and Lake, there's a huge section of algae bloom. It was gross. Yeah, it does happen, especially in kind of large centers. This is kind of an interesting graph, and if you kind of think of what we've been talking about a little bit today, maybe you can explain it or help me explain it. So this is a world population going back about 1,000 years. So this is 1,050. Population of our planet's been about 500 million. And then in about 1850, we hit 1 billion. And then 1950, in this area here, the Industrial Revolution happens and the population starts to skyrocket. And this is a projected population to 2050. Right now we're at about, I think we're at 7 and a bit billion people. So we're right around here right now. What happened right here to cause this big boom in population? You know, we're kind of cruising along, 500 million, then we kind of got up to 1 billion, then it's like, kaboom, we get this huge population growth. What happened on our planet that allowed us to do this? And there's not a one right answer, there's a bunch of right answers. There's a bunch of things that kind of all happened at the same time. If you think about what we've been talking about in terms of nutrients, can anyone kind of maybe explain in terms of nutrients how this happened? What do people need to live? Well, we need these nutrients. We need these cycles. So we need phosphorus, we need potassium, phosphorus, carbon, and nitrogen. We need these to live. So we have medicines. That's a good one. So that happened in the Industrial Revolution. We were starting to be able to produce medicines more effectively. One of the big causes of this population boom was fertilizer. If you look when fertilizer was invented, it was right around here in this Industrial Revolution. Without fertilizer, we couldn't sustain enough population. But now that we can trap all these nutrients and put them onto our fields, then we can, feed more people. And the population of the earth has increased dramatically as a result because we've been able to trap all these nutrients, put them into a solid form, put this on our fields. You imagine living 200 years ago, the food that you grew was the food that you ate. If you didn't grow any food in the summer, you'd die. That was just the reality of it. So that's what kept our population for so low for so long. Then we get to a point where we can all of a sudden mass produce foods and people have more babies because they can afford to, keep them alive and things like that. And you end up with these big population booms. So that's kind of one of the ideas. You end up with all of these fertilizers, increasing the food production and supply, and you end up with a big jump in population. So that's kind of the big thing there. This is the last slide, and then we'll take a bit of a break, and then we'll take up some bioaccumulation stuff after the break. So any significant changes to any of the nutrients, carbon, hydrogen, oxygen, nitrogen, or phosphorus, can impact biodiversity. So we talk a bit about climate change, global warming as a result of messing with the carbon cycle. We have increase in global temperature, water levels increasing. You end up affecting the food webs in many ways. So increased levels of nitrogen and phosphorus lead to this idea of eutrophication, allowing species to thrive where they possibly shouldn't be able to because of increased amounts of nutrients in the soil. So some organisms will benefit, plants and animals alike, by increased levels, but that's not necessarily a good thing. They might not be able to naturally survive in that area, but now we're allowing them to. So now they can offset the food chains and webs and things like that. So there you go. So that's kind of nutrient cycles and biodiversity. So that's the first sort of section we're going to get through today. I'm happy I got through it that fast. It did take a while, and I apologize that it is kind of boring stuff, but there you go. The key here is that you can look at the learning guides and go from there. So it is, it's looking about 10:20, no, 9:20, 10:20, 10:20. Got it. Let's take a 10-minute break, and then we'll come back and we'll talk about some bioaccumulation and biomagnification. So I'm going to introduce an assignment. We'll talk a bit about the next section. It's super short, so we won't take the full hour after this. So take a break, go grab a cup of tea or a snack, and I'll meet you guys back in 10 minutes. Thanks. Hi guys, welcome back. If you want to give me a green check mark, make sure you didn't lose anybody along the way, or you're still getting that cup of tea, or at least slow kettle or something. Thank you. All right, so while everyone's kind of checking in here, behind me you can see Unit 2, Ecosystems, is kind of where we've been working our way through. We did energy flow and ecosystems on, I guess it would have been Wednesday last week. That seems like a long time ago. Today we did nutrient cycles, so you should go through there. There's a quiz in there, and there's a crossword for the vocab. You should practice on both of those. And then we had bioaccumulation, which we're going to do here in a second. But before we get to that, there is an assignment that I'd like you guys to do. Now, this nutrient cycle stuff can get really, really boring and really, really dry. So I'm trying to spice it up a little bit, help you guys maybe look a little bit at the nutrient cycles in your data booklet. And I'll bring up the assignment here, and then you guys can have a look. And I want to mention a few things about it. So this is kind of separate to the learning guide and separate to everything else. What I would, I'll just blow that up a little bit so you guys can read it. This is a biography of a nutrient. So maybe you've done something like this before with perhaps the water cycle in grade 7 or 8 or whenever you do the water cycle. This is the biography of a nutrient. So what I want you to do is pick one of the 3 cycles. It doesn't matter which one, nitrogen, carbon, or phosphorus. And I want you to kind of talk about the journey an atom would make going through the cycle. So how long it's going to take at each place, you know, where it goes through, how humans have influenced it. These are all kind of things you should include in there. Now, I'm going to leave the method of your biography wide open. You could write a story. You could go and use like a web tool and do like a comic sort of thing if you wanted. I don't really care what it looks like. The idea here is that you can describe how this atom has moved through the cycle. So pick any cycle you want. Kind of try to do a full cycle. And this is the rubric we'll use to mark it right here. So kind of at the low end, most required parts described accurately, or if all elements present, some not accurately represented. All parts to describe thoroughly is fully meeting and exceeding all parts and some additional parts described accurately through the sort of cycle. So it's not meant to be this like big, long, arduous thing, just kind of a fun way to look at one of these cycles. So pick a cycle, pick somewhere to start. You could be nitrogen, you could start in the atmosphere, you could get fixed by lightning, or you could get fixed by bacteria, then you enter the soil, and then maybe you get nitrification happening. You change into NO2, NO3, get taken up by a plant, get in the plant, get eaten by a deer. Now you're in the deer, and then maybe you die and go back into the soil or something like that. So just pick one of the cycles, pick a spot to start, and just kind of follow the cycle through and see what happens next, and describe it along the way. Make sure to include things like times. If you can, include a human impact in there. It'd be awesome. So those are the kind of the criteria, some basic things. You could talk about things like bonds if you want, if you're a little into the chemistry sort of aspect, but generally speaking, you're just going to kind of follow the nutrient through. So story would be good, pretty basic. You could do something a little more adventurous if you wanted. If you have an idea of something you want to try and you're unsure if I'll like it or not, just, you know, send me a message and I can say, hey, that's a great idea, or maybe do this or that. Does anybody have any questions on that assignment? I would like it to be done this week. I mean, we're going to be finished Unit 2 right now, so I'd like this to be done at the end of the week for sure. Anything? When do we need to hand it in? Let's go with Friday. Does Friday work? Gives you a week to do it. Seems like more time than you'd probably need. Probably an afternoon, maybe half an hour. Could get this done. There we go. All right, so nobody has any questions. We'll just continue on. This last unit section is super short, and it basically has these kind of two big ideas, bioaccumulation and biomagnification. And then that kind of ends the second chapter, or second unit. So bioaccumulation and the ecosystem. So the idea here is that we're going to start talking about sort of pollutants and things like that. And this is a picture of a frog, and this frog has 3 legs, which you'd think, cool, that could be a good thing if you were a frog. But no, it's not a good thing. The idea is this. Basically, during the Industrial Revolution, we started using chemicals to do things, and we would just use them, and we didn't really know what they did, if they were good or bad. We just kind of used them because they worked. And then all of a sudden, here we are, 50, 100 years later, and we're thinking, hey, that frog has 3 legs. There's something wrong with that frog. So along the way, a lot of the chemicals that we used ended up causing a lot of harm to the environment, but not immediately. We're talking about sort of longer term impacts. So the idea is we're going to look at these sorts of impacts here today, and we have some fancy sciencey words to describe them, and we're going to go with that. So since the 80s, a lot of amphibian species have declined in population numbers. Now, amphibians are special. We talked a little bit about beavers and salmon being keystone species because they live in water. And amphibians are the same. They live on land and water. So they're in the water, they're in these chemicals, and these chemicals get absorbed into their bodies all the time because they're just sitting in that water, and the chemicals are in the water and they get absorbed. And then the amphibians will enter the food chain from there. So we're going to look at how that works today. So the first idea is bioaccumulation. This is kind of the big idea for this section. Basically, the problem with the toxins, and we're going to talk about lots of different ones, but all of them together, if we just lump all of these pollutants together, once they enter an organism has no way of dealing with it, no way of getting rid of it. So if you were to eat some lead, it's in your body now, and your body can't deal with it. It doesn't know what to do with lead. It just, over sort of millions of years, our body's never encountered it before, so it's never had to deal with it. But now all of a sudden we're releasing all these chemicals into the environment. So if you can think for a second about the arrow here, if you start at the very far end, you have these little tiny fish or plankton or whatever at the bottom of the food chain. And let's say they all eat one pollutant. Doesn't matter what the pollutant is, but they all end up with one inside their body. And it's not fatal if you have one. It's just like one, no big deal. So then these fish get eaten. Maybe this fish eats 2 of these small fish each day. So now this fish is the next step in the food chain. It has 2 because it ate 2 of these fish. And then this big fish here eats 4 of these smaller fish each day. So now it has 4. And then the big fish, eats 2 of these fish a day. So now it has 1, 2, 3, 4, 5, 6, 7, 8. And as you go up the food chain, you end up with higher and higher concentrations of the chemical until it becomes fatal, or it affects that organism to the point where it's sick or dies. And again, the problem is these organisms can't get rid of these chemicals. We have no way of getting the chemicals out of our bodies. And the chemicals last for really, really long times. So this is an example of bioaccumulation. As you move up a food chain, the concentration of chemicals gets bigger and bigger until it has an effect on the organism. So generally speaking, the very far end here, you're not going to have any sorts of effects because the organism only has one chemical in it. But as you move up the food chain, you get closer to the top level, the concentration increases, and you end up with really high levels of contaminants. So the idea is the chemical gets passed along the food chain. As you move up, you increase the concentration. Now, coming back to the idea of a keystone species, if we're talking about pollutants like this in a salmon, now those salmon spawn into the interior of BC, they die, bears eat them, eagles eat them, all sorts of animals eat them. They are now taking in these really high levels of chemicals because salmon are pretty high up the food chain. You end up with keystone species having a huge effect on the ecosystem as a whole. So that's bioaccumulation. Accumulate, you guys know what the word accumulate means. Bio is living things. So something in living things is accumulating, bioaccumulation. At the same idea, you end up with this biomagnification. So the higher you get up the food chain, the more concentration of chemical exists. So that's what the picture here behind me is showing. You see bioaccumulation. At the very bottom of the food chain, very low levels of contaminants. So find my mouse here. Up here, really nothing at the bottom of the food chain. Then you get a little higher because these guys eat a few of these guys each day, and you end up with a little bit more. And then these guys eat a few of these guys, and by the time you make it to the top of the food chain, the amount of chemicals is really high. So there's bioaccumulation on the top, and then biomagnification's at the bottom. The amount of chemical, you start at krill at the bottom here. These guys eat the krill, then the walrus eats it, and then you get to the polar bear that eats the walrus, and you end up with really, really high levels of contaminants at the top of the food chain, or food pyramid. So that is biomagnification. So these are the two ideas. Bioaccumulation is chemicals get into the systems, and then as bigger and bigger things eat them, as you go up the food chain or food web or food pyramid, the concentration gets higher as you go up because each successive level has a higher concentration. So those are the two big ideas there. An example that's kind of local to us is PCBs. So polychlorinated biphenyls, I think is PCB. It's an acronym. And basically, in the 70s and 80s, PCBs were in almost all electronics that we made. It was a good conductor of electricity, it was an insulator, it was all these great things. So we put all these PCBs in these electronics that we used, and then what happens when you're done with your electronics? Well, you throw them away and they enter the landfill. And if you have some parts that you replace, you throw them away, and then all of these PCBs entered the food chain. So they entered the water table flows out to the ocean, and then it affects, all of these animals at the very basic level. So the idea here is that at the very bottom of the food chain, you have all these little tiny bacterias, and they maybe all absorb one PCB each. And then this little krill here, he eats about 100 bacteria a day, so now he has 100 contaminants in him. And this lovely perch-looking fish here, it eats like 10 krill a day, so now it's got 1,000. And then this eats, 2 of these, so now it's got 2,000. And the orca eats, 5 of these. So now we're up to 10,000 by the time you make it to the orca. And basically the problem with the orca whale is these PCBs affected their ability to have their reproduction abilities. So once the orcas were really highly affected by these PCBs, they weren't able to have viable offspring. So the numbers of orcas just dropped dramatically because these PCBs we were putting into the environment. So it's estimated that the PCBs that we don't use them anymore, but we estimate that it'll have an effect on orcas' life cycles until at least the year 2030. That's how long they're in the environment. So we're thinking 1977. It's about 60 years, just under 60 years, that these chemicals, by the time we figured it out that they're a bad thing, 60 years later, they're still there. So that was just one example, PCBs in orca whales in BC. Another one is DDT, and now I'm not even going to pretend to know what DDT stands for, but it's still used in a lot of places in the world. And basically, you can see a little image here where they're just spraying DDT on the beach because it gets into the water and it kills mosquitoes, because mosquitoes are vectors for diseases. They transfer lots of diseases and things like that. So 1941, it was introduced to control mosquitoes, and they still use it in lots of places in the world. But it has the same effects on the environment, this biomagnification and bioaccumulation on the environment. And basically, its kind of impact in our area is with this bird here. This is a peregrine falcon. So peregrine falcons used to live in the Okanagan, and then they went completely extinct. The problem was this. In the Okanagan Valley a long time ago in the 40s and 50s, we would spray this DDT into like ponds and marshy areas to kill the mosquitoes so we wouldn't have to deal with mosquitoes. And it entered the food chain. And as we know, as you get higher and higher up the food chain, you end up with problems. So DDT doesn't have any sort of immediate impacts on humans. That's not good for you, but it's not going to kill you immediately. But as we get up the food chain, you end up with problems. So these falcons would lay eggs, and the DDT that was in the falcons, as it bioaccumulated to the top of the food chain where falcons are, would make the shells of their eggs very thin. And every time a falcon would sit on its eggs to kind of try to incubate them, it would actually crush the eggs that it laid, and then it would have no offspring until they completely went extinct in our area. So this is a picture down here in the bottom of the eggs of these falcons. And this wasn't just a falcon problem, this was almost all birds. This DDT would enter, it's chemical, Taylor, sorry, I should have mentioned that. Just a chemical used to control bugs. It made the shells really thin, and we saw really sharp declines in all of the sort of bird populations, and even some went extinct. So we've reintroduced them now that we don't use DDT in the Okanagan anymore. The birds live in the valley, live in Kelowna, and the population's starting to increase again, but here we are. This was 1941, it was started. We're 60 years later, we're still dealing with the same sorts of issues. These chemicals exist, and we can't get them out of the environment. Once they're there, there's nothing that can naturally break them down, and they're there forever. So that is kind of the problem with these POPs, persistent organic pollutants. So POPs are persistent organic pollutants like DDT, PCB. There's lots of acronyms in this unit. So that's a problem. No organism can break them down. So it's a bad thing. Why don't they fade away? That's a really great question, Alex. DDT is bad. Why don't they just fade away? They're created by humans. They're not naturally occurring. So if something was naturally occurring, something in nature would be able to deal with it. That's how sort of evolution's happened over, millions of years. Something develops, a toxin, there's going to be something that develops a resistance to that toxin along the way. You have all these natural interactions that happen over long periods of time. But with things like DDT and PCBs and Agent Orange and all these chemicals that humans make, we've just created them. And there's nothing in nature that's had enough time to figure out a way to defend itself from them. So because we have created them and nothing can deal with them immediately, we end up with these huge problems. So let's talk about heavy metals. This is another one. If you think about it, metals are stuck in rocks. They should, if humans had no impact on the environment, the metals should just be in rocks, and I shouldn't have a metal watch, and my ring shouldn't be on my hand, and all the cameras and things we're using, TVs, should just be part of a rock somewhere. So what we do as humans is we say, hey, I like metal. We can make stuff out of it. It's pliable. I can make a TV and the circuitry and wires in your house and all these cool things. So we take the rocks, we take them out of the ground, we crush them up, we melt the metal out, and we use it. Well, it turns out that a lot of these metals are bad for us. So lead, mercury, cadmium are the kind of worst polluting heavy metals. Lead, this comes back to the idea where lead melts at a very low temperature. They used to seal tin cans, like you go to a grocery store and get a can of something, it used to be sealed with lead on the top because it was so easy to melt lead. Before we knew lead was bad for us. So it was really common to have lots of lead in your environment. We put lead in paint to give it that really nice yellow color. Lead was everywhere. It's bad for you, turns out. Who knew? No one. Now we know. So a lot of electronics can contain lead. Old houses will have lead-based paints. You end up with these lots and lots of lead in the environment. And again, we pulled it out of rocks. It shouldn't be here, but it is. So you end up with this runoff. It enters the water system, and then it enters your food chain all the way along the ground. And animals eat it. They take it in. It causes nervous system damage, reproductive damage. Not good. So that's lead. What's the next one? Cadmium. Cadmium, again, happens at sort of low levels in nature, not a big deal, but it is natural. But if you, Alex, could imagine going out to your backyard and picking up a rock, well, there's probably some metal in that rock, but how much is it? How much concentration's there? You literally have to, crush tons and tons of rock up to get the metal out of it. So the problem isn't that it exists naturally, it's that it exists at very low levels naturally, and then we take millions of tons of rock, we melt it down, we pull the metal out, and you end up with these toxic chemicals. So the problem with cadmium isn't necessarily that we ingest it or anything like that. It is mainly found in cigarette smoke. We know that smoking's bad for you, and this is another reason why. So you end up with this heavy metal, cadmium, in the smoke. It affects your kidneys, it affects your lungs. Generally a bad thing. It's toxic to earthworms, causes health problems in fish. We have this food chain issues. So there's cadmium. And the last one's mercury. Again, we used to use mercury for all sorts of things, and it's pretty useful metal because it's a liquid at room temperature, which is actually pretty uncommon. There's only one or two, I want to say two, metals that are liquid at room temperature. So we used to use it in, I know I had a house, my first house that I bought, it was built in the 50s and had a thermostat. So basically there was just a little dial that you turned, and inside the thermostat was a mercury switch, and it would tip over, and the mercury was in this glass tube, and it would connect the switch depending on which side the thing tipped. So we use mercury for all sorts of things, like fillings in your teeth, you use mercury. You use mercury to pull gold out of rocks, and all sorts of mercury uses. It's a useful thing, but it's bad for you. So basically, when we pull fossil fuels out of the ground, they have really low levels of mercury. It gets in the atmosphere, it rains down, now it's in the food chain. The problem is that it enters the food chain and it bioaccumulates. So if you are a pregnant woman, my wife was obviously just pregnant not long ago, my son's 5 months old now. When she was pregnant, she wasn't allowed to eat any raw seafood because seafood has really high levels of mercury, or it can. You talk about these sort of top level carnivores like tuna and things like that, fish, high level on the food chain fish, they have really high levels of mercury in them. And once that mercury gets into your body, it's not good. Mercury also causes birth defects. That's why it's such a huge issue for pregnant women. So coal burning is the sort of the greatest increase of mercury, and it kind of bioaccumulates in your brain and your kidneys and your heart, these really important organs in your body, and it can cause some bad things. So there you go. Sorry, Alex, you had a question here. How cold would it have to be to freeze liquid? How cold would it have to be to freeze liquid nitrogen? I don't know what the freezing point of nitrogen is, but a quick Google search will find it, I'm sure. Now I've lost my place. All right. So the idea here is, how can we reduce these effects? One way, it kind of seems silly, but if you can trap these heavy metals, if you can trap them in the soil, and then the soil is going to kind of get compacted over millions of years, and then now these chemicals get locked in sort of rocks and things like that. So if we can get them back into rocks somehow, that would be a good thing. It's not going to happen in the short term. We're talking thousands and thousands and thousands and thousands and thousands and thousands of years, but we can trap them that way. So there's no sort of immediate thing we can do. So that would be great if we could trap it. There's this other thing called bioremediation, and remediation is trying to fix up the environment to make it better. Bio is living things, so using living things to fix up the environment. The picture behind me here is from the Deepwater Horizon oil spill catastrophe in the Gulf of Mexico I can't even remember what year that was. It was probably within the last 10 years though, for sure. There was a deep well that they'd been digging. The actual rig lit on fire, exploded, and then the oil was just leaking right into the Gulf of Mexico and to the surface, and you get these big surface oil slicks, which turns out wasn't such a bad thing because it evaporated. But you could imagine what they did was they sprayed a bunch of chemicals, this is called dispersants, basically making the oil sink to the bottom and land on the seafloor, and then just hoping it would get covered up, and eventually, after a long period of time, it would get covered up and that oil would make its way back down into the ground so no organisms could be affected by it. What they did up on the surface, especially the beaches in the Gulf of Mexico, is they sprayed this stuff. It's a type of bacteria, and it can take that oil and it can break it down. And it basically is bacteria that eats oil. The bacteria takes these really long hydrocarbon chains and it breaks it down into really small hydrocarbon chains into things that can be useful in the environment or not as poisonous to the environment. So that's what bioremediation is, using living things to try to basically eat. It's what it's doing is eating the oil, turning it in from something that's poisonous to something that the environment can handle. So they did that in the Gulf of Mexico recently. The last kind of thing we're going to talk about here is the red tide. Now, Taylor, I know you're down in the lower mainland. This happens every once in a while in the summer in off the coast of BC. It's called red tide. Basically, the temperature gets really high and this big red algae bloom happens. All the water kind of turns this reddish color because of all these algae that are there. And then the organisms like clams and things that are filter feeders, they take in all this red algae and then they become poisonous. Now, if you eat those clams or oysters or whatever it's taking in this red algae, it can kill you. It's really toxic for humans. It's called red tide. Happens every once in a while. And if the conditions are right. So the shellfish can eat it because it's low concentration level in them, but if you eat like 3 or 4, now you're going to get sick because of bioaccumulation, biomagnification ideas. So it can be deadly to a human. There you go. That is bioaccumulation, biomagnification in a nutshell. Basically, 2 big ideas there, biomagnification, bioaccumulation. And if I go back, this diagram kind of sums it up. And they're both really closely related. You end up with the contaminant level increasing as you go up the food chain. That's kind of the big idea here. And that's kind of it. There is some questions that'll refer to the different organic pollutants like DDT and PCB. There is questions that'll talk about the heavy metals, cadmium, lead, and mercury. Those are the 3 big ones. So you do need to know a little bit about that sort of stuff, but there's not a huge concentration on it. So just be aware of that. I'm just going to bring up chat here for a second. So there you go. I knew Taylor would have all the answers for me here. So yeah, if you're fishing for crab down in lower mainland during sort of red tide periods, you're not allowed. They close all the shell fishing industries down and don't allow people to go out. And it seems like every time they do it, somebody's like, oh, it's not a big deal. I eat this stuff all the time. And then they'll eat it and they'll get really sick and die as a result of eating this affected stuff. So there you go. Alex, is it possible for a gas to go straight to a solid and skip liquid? Yes, it is possible. This happens every morning this time of year on your lawn. If you wake up and there's frost, it didn't rain, and how did that solid water get onto the roof of the house across the street or the grass on your lawn? Well, it was a gas in the atmosphere, it was cold enough, and it froze on the roof of your house or whatever. So that happens all the time this time of year. That's what frost is. Taylor's asking, should we finish off this booklet? Yeah, we should. Now, I realize some of you aren't even done Unit 1, which is why I told you to get it done last week. And now we are done Unit 2. So we are cruising. And I'm happy as to where we are, but we unfortunately need to keep kind of cruising at this sort of pace for a little while. So we're done Unit 2. Should we do the case study of nitrogen loading in the learning guides? That's a good question. Let me have a look. I didn't see that. Get out of here. So biography of a nutrient, I'd like you guys to do that for Friday. Unit 2 learning guide is what you're talking about, Ava. Do you have the page number for that, Ava? Probably tell me, find it faster than if I tried to do it myself. Page 529. Herbivore, carnivore. It's probably in the bioaccumulation section. Phosphorus cycle, nitrogen cycle. It starts in 18 and goes to 23. It was getting warmer. 14, 15, 16, 17. How can the excess levels of nitrogen be reduced in the Fraser Valley? Table shows the number of kilograms of nutrient required by corn and grass for each hectare of plant each year. Which crop requires less nitrogen? Okay, has anyone done this? Has anyone finished it? Yeah, Anna, I'm just going to figure that out right now. Has anybody done this nitrogen questions out of the learning guide? No? Negative? If you've done it, speak up, else I'm going to say we don't have to do it. Okay. Let's not do it then. So don't do pages 18 to 23, and let's do the biography of a nutrient instead of this, just so we're not kind of overloading you guys with work. So what page does that go to? Conclude and apply. Yeah, so 18 to 23. So we're not going to do pages 18 to 23 from the learning guide. Instead of doing those, we'll do the biography of a nutrient instead. So that would be good. And that would be less work for you guys and less work for me, and I think that's probably a fair compromise. I'm looking forward to the biographies of a nutrient. So we're done Unit 2. When should we be finished this? I don't know. What do you guys think's fair? I'm not going to see you again until Wednesday. We're going to have another double block. That's a good question, Alex. Should we do the first 17 pages of the learning guide? You should do the whole learning guide. The whole thing should be done now. I should rephrase that. You should be able to do the whole learning guide. You don't need to be done right now. But pages 18 through 23 don't need to be done. So I'll put a note in the learning guide up at the top, and hopefully I can clarify that so some people don't end up doing both. Ava, yeah, descriptive paragraph would be good. Whatever you want, however you want to do it, I would be happy to kind of accept that. The Unit 2 stuff. Now, I'm going to see you guys on Wednesday's class for another double block. So, how about this? I will give you guys till the end of the week to finish off this Unit 2 stuff with both your biography and the learning guide. So those kind of two things. But if you guys have any questions about the learning guide, I need to give you guys a chance to ask them. So we'll allow that next day. So on Wednesday, I won't see you until Wednesday. On Wednesday's class, if you have questions about the learning guide, you can ask them then. If you don't have any questions about the learning guide on Wednesday, I'm going to assume that everybody just thought it was the easiest thing ever and it's done. And I think that seems fair. And then I won't see you after Wednesday's class till the following week. So let's get this Unit 2 stuff done, all of it for Friday. That seems fair. And then on Wednesday's class, we'll answer any questions you have, and then we'll jump right into the Unit 3 stuff. So does anybody have any issues with that? Does anybody have any questions? Am I unclear about that? So Unit 1's done. You were supposed to be done that on Friday. Unit 2 now is where we're at. We should be done that by, well, you should be done by next class, but I'll give you till Friday because I'm a nice guy. You're welcome. And we're going to start on Unit 3 on Wednesday. So if nobody has any concerns, issues, comments, yeah, so the test should be done by Friday. That would be good. So Unit 1 test was last week. Unit 2 test is this week. And this is kind of the pace that the course goes. There's 10 units. Some of the chemistry stuff gets a little bit longer. The biology stuff's a little bit quicker. So we end up doing about a unit a week. And that's kind of it. And then we get spring break in there, kind of messes with stuff in a few weeks. So that's kind of where we're at. I'm going to leave it there. I will see you guys on Wednesday. If you have any questions about the learning guide or biography or nutrient or anything like that, feel free to ask. And we'll go through anything you have next day. And hopefully you can get all of this Unit 2 stuff wrapped up by Friday's class. And that's it. We'll see you guys on Wednesday. Thank you.